thank you so much for inviting me to give a talk in this conference. So my talk will be on some non-vanishing results for L functions associated to cubic characters over function fields, and this is joint work with Chantal David and Mathilde Laline from Montreal. So I want to start by giving some background. We are interested in L functions associated to characters of a given degree, of a given order. So a Dirichlet character is a completely multiplicative function defined, if it has modulus d, it's defined on integers modulo d. It takes complex values. Completely multiplicative means that if I have any two elements a and b, then chi of a times b is equal to the product between chi of a and chi of b. We extend this character to all integers by periodicity, and we have the property that the character is equal to 0 whenever the GCD between the modulus d and the integer a is not 1. And we call the character primitive with conductor d if d is the smallest modulus for which chi is a character modulo d. So in some sense, the character doesn't come from any smaller character. So once we have the Dirichlet character, we can define a Dirichlet L function. When the real part of S is bigger than 1, then the L function is defined by the Dirichlet series of chi of n over n to the s. And this has an infinite Euler product representation over primes of 1 minus chi of p over p to the s inverse. And the L function has some very nice properties if the character is not principal. So this means that it's not equal to, doesn't only take values 0 and 1, then it can be analytically continued to all complex numbers. And the L function has a functional equation, so we can relate the value of the L function L of s chi to the value of L of 1 minus s chi bar. So chi bar is the conjugate character. And one question that we care about in the field is the following. So we are interested in the value of the L function at the special point 1/2, which is the center of the critical strip. So the question is, can the L function vanish at 1/2? In general, the philosophy is that an L function should vanish at this special point for some special reason. So for example, the Burchard-Swinnerton-Dyer conjecture predicts that the order of vanishing of an L function associated to an elliptic curve should be the rank of the elliptic curve. So here there would be a very special reason for the L function to vanish. Now for these Dirichlet characters, we don't really believe that there should be a special reason for the L function to vanish. So a conjecture of Chawla says that the L function should never vanish at the point 1/2 for any Dirichlet character. Now this is a very strong conjecture. We're quite far from proving the full Chawla conjecture, but we can prove some partial results towards it. So one interesting question is, let's say that we restrict to some special characters. So what happens, for example, if we restrict to quadratic characters? So quadratic characters are characters for which chi squared is equal to the principal character, which just takes values 0 and 1. And quadratic characters are studied a lot because they have very nice arithmetic applications, for example, to class numbers or ranks of elliptic curves. So what happens if we restrict to these special characters, or what happens if we restrict to cubic characters? So we will denote by chi d the quadratic character with conductor d. And it turns out that one way through which we can study these non-vanishing questions is by considering moments in these families of L functions. So what does this mean? Well, now if I just restrict to quadratic characters, I want to obtain some asymptotics, or I want to study the kth moment in this family of quadratic L functions. So I'm averaging over discriminants d of size up to x, and here I have a star on the sum, which means that I'm summing over primitive characters, and I'm taking the kth power of L 1/2 chi d. It turns out that if we can understand something about these moments, then we can say something about non-vanishing. So there is a conjecture due to Keating and Snaith, which says that the kth moment should be asymptotic to x log x to the power of k times k plus 1 over 2 times some constant ck. And for a long time, people didn't really understand what ck should be. And then Keating and Snaith had the idea of using random matrices to model these L functions, and they predicted the precise value of ck. It turns out that computing moments is usually difficult, and we can't compute too many of them. So for the quadratic L-functions, the first two moments were computed in the 80s by Utila. Later in the 2000s, Soundararajan computed the cubic moment, and he also improved Utila's result on the second moment. He obtained some lower order terms. And then there was later work of Diaconu, Goldfeld, and Hofstein, who also obtained the cubic moment, but using completely different techniques. So they used multiple Dirichlet series. And very recently, Shen computed the leading order term for the fourth moment. This is conditional on the generalized Riemann hypothesis. And he used ideas of Soundararajan and Young, who worked in a different family of L-functions. So this is what we know in terms of moments. Now, what does this tell us about non-vanishing? So it turns out that if we know the first two moments, it's relatively easy to get some proportion of non-vanishing. So directly using the asymptotic formulas for the first two moments, Utila showed that the number of discriminants of size up to x for which the L function is non-vanishing is bigger than x over log x. So we know that there are roughly x discriminants up to size d. But we would want to be able to say something stronger, so we would want to be able to say something like more than some constant c times x of these discriminants have L functions non-vanishing. So Soundararajan, in the same paper where he computed the second and the third moment, he also showed that actually more than 87.5% of the L functions are non-vanishing at the critical point. And he called he proved this using the mollifier method, which goes back to using moments. So I want to describe the mollifier method a little bit because it will be important in what I'm going to talk about later. So mollifiers have been used for a while. They were used, for example, by Selberg to show that the positive proportion of the zeros of zeta lie on the critical line. So the idea of Soundararajan was the following. For this setting of quadratic L functions, he defined a Dirichlet series M of chi d, which in some sense, you want this Dirichlet series to behave like the inverse of your L function. So you want it to behave like 1 over L of 1/2 chi d. And then when you compute the first mollified moment, you want to show that this is asymptotic to some constant times x. And more importantly, when you compute the second mollified moment, you want that to also be asymptotic to x. So let me remind you that when we computed the unmollified moment, so if I don't have the mollifier here, then I expect to get an x times log x cube. And now what this mollifier does is that it sort of behaves like 1 over your L function, so the second mollified moment also doesn't grow. It's just asymptotic to C2 times x. So the question is, how do we define the mollifier? And with this kind of heuristic in mind that you want the mollifier to behave like the inverse of your L function, then you can define it as a series over integers L going up to some point, which depends on the conductor of the size of the conductor. In this case, you can go up to roughly square root of x. And then you have mu of L over square root of L times the character. So mu of L is the Mobius function. And this behaves like 1 over the L function. Now, this is not precisely the mollifier that Soundararajan used, but it has roughly this shape. So using this and then directly using Cauchy-Schwarz yields the 87.5% proportion of non-vanishing, which is a pretty good proportion of non-vanishing. Okay, now when we move on to cubic L functions, again, we're interested in the same question. If I have a cubic character and I have the L function associated to the cubic character, is the L function equal to 0 at 1/2? And how often can it happen? We can also answer this question by studying moments. So let's say that now we are in the family of cubic L functions. There's a conjecture using the so-called recipe method of Conry, Farmer, Keating, Rubinstein, and Snaith. So these authors developed the so-called recipe to predict asymptotic formulas for moments in various families of L functions. Their methods are very robust, so they work in many families. And using their approach, we can conjecture that the kth power of L1/2 chi, when we sum over primitive characters mod, cubic primitive characters mod q, and we also sum over the conductor q, which goes up to size roughly x, then actually these moments do not grow. So they are asymptotic to some constant bk times x, and then we have some power saving error term. Now, in terms of actually computing these moments, these are harder to compute than moments of quadratic L-functions. So here we can only compute the first moments. Let me remind you that for quadratic L-functions, we can compute the first 4 moments. So the first moment was computed by Bayer and Yang. They considered the smoothed first moment. So here we have this weight function, W, and this roughly means that I'm summing over conductors of size up to x, and they have this leading order term of size x, and then they have this power saving error term. Now, the second moment seems to be out of reach with current techniques, so you can't really use the mollifier method here. So what Bayer and Yang did is they considered upper bounds for higher moments of these L-functions. And using these upper bounds for higher moments of L-functions, they showed that the number of primitive cubic characters of conductor of size up to x, for which the L-function is non-vanishing, this is bigger than x to the 6 over 7 minus epsilon. So this is pretty far from a positive proportion. Now, if we assume, for example, the Lindelof hypothesis or the Riemann hypothesis, one would be able to show that more than x to the 1 minus epsilon of the L-functions are non-vanishing.
Alexandra?
Yeah.
There is a question. Could you remind us what does the star on sum symbol mean?
The star means that I'm summing over primitive characters.
Thank you.
Yeah, so whenever I have the star, the sum is over primitive characters. Yeah, so we would like to be able to say that more than some constant c times x of these L-functions are non-vanishing. Okay, now this is the situation over number fields. So now I want to switch gears and talk about the function field setting before defining these problems in this setting. So when we work in function fields, there's usually this kind of nice dictionary between the integer setting and the function field setting. So we can think of monic polynomials with coefficients in fq of t, the ring of polynomials with coefficients in fq. We can think of these monic polynomials in fq of t in analogy with the positive integers. Then the norm of a polynomial, this is defined to be q to the degree of the polynomial, that would correspond to the absolute value of an integer. Then monic irreducible polynomials would correspond to primes in the integer setting. Square-free polynomials would correspond to square-free integers, and so on. So with this kind of analogy in mind, we can define many of the classical objects in this function field setting. So for example, the Riemann zeta function is defined by the Dirichlet series 1 over n to the s when the real part of s is bigger than 1. Since we said that positive integers correspond to monic polynomials, then we will define our zeta function in this setting as the sum over monics of 1 over the norm of f to the s. And here we can actually compute the number of monic polynomials of a given degree. So if I look at polynomials of degree n, there are exactly q to the n monics of degree n. So the zeta function just becomes a geometric series, and it turns out to be equal to 1 over 1 minus q to the 1 minus s. So it's pretty simple, and we have a simple pole at s is equal to 1. And usually for the function field setting, it's more convenient to work with a different variable u, which is q to the minus s. Then the zeta function becomes the sum over monics of u to the degree of f, and this is just 1 over 1 minus qu. So we have a pole at 1 over q. Okay, now we can define the L-function. So if we have a primitive character modulo of polynomial h, then the L-function is defined similarly as over the number field setting, L of s chi. Again, I want to use the variable u, which is q to the minus s. So L of u chi is the sum over monics of chi of f u to the degree of f. And this has a product, an infinite Euler product representation in terms of monic irreducible polynomials p. Now the L-function satisfies some nice properties. So if chi is not a principal character, then the L-function turns out to be a polynomial. And the polynomial has degree, at most, the degree of the conductor. It also has a functional equation. So for example, I wrote here the functional equation for an L function associated to an odd primitive character. So we can relate L of u chi to L of 1 over q u chi bar, where again chi bar is the conjugate character. So this is the same as relating L of s chi to L of 1 minus s chi bar. And here omega of chi is the root number. This has absolute value 1. And it will be important in what I'm going to talk about next. Moreover, the L function has a very nice property, which is the fact that we know that the Riemann hypothesis is true in this case. So the non-trivial zeros of this polynomial, all the non-trivial zeros lie on the circle of radius 1 over square root of q. Okay, so now the kind of questions that we're interested in are similar to the questions over number fields that I described before. So a natural question would be, is Chowla's conjecture expected to be true over function fields? Let me remind you that Chowla's conjecture in the number field setting was said that L of 1/2 chi is never equal to 0 for any Dirichlet character. So then the question is, if I take some Dirichlet character chi over function fields, is the L function non-vanishing at the point 1/2? Again, let us specialize to quadratic characters. So if we look at quadratic characters over function fields, in joint work with Hang Bui, we showed that more than 94% of these central values are non-vanishing. And I should say that this is achieved not by computing moments, but by computing the one-level density of zeros in this family of L functions. So I'm not going to go into details of what computing the one-level density of zeros means. I will just say that this roughly means that we're looking at zeros in the family of L functions, zeros which are close to the point 1/2. And it turns out that if we can understand something about the zeros which are close to 1/2, then we can see something about non-vanishing at 1/2. However, one very interesting aspect of function fields is the fact that it turns out that the analog of Chowla's conjecture is actually false over function fields. So Wan Lin Li showed that if we look at L functions associated to quadratic characters and we let the family have size roughly x, then more than roughly cube root of x of these L values can be equal to 0. So this is different from the number field setting. Notice that this is a small proportion of vanishing. It is still expected that 100% of the L functions are non-vanishing. However, they can vanish. Okay, now in terms of cubic L functions, just like in the number field setting, we can say much less about non-vanishing for cubic L functions. So last year, in joint work with Chantal David and Mathilde Laline, we obtained an asymptotic formula for the first moment in the family. So here I'm taking Q to be congruent to 2 mod 3. This is the so-called non-Kummer case. So this means that we don't have cubic roots of unity. And I'm summing L1/2 chi, and I'm summing over primitive cubic characters of genus G. So this roughly means that I'm summing over characters whose conductor has degree roughly G. And we get an asymptotic formula with a main term of size roughly q to the G. So I wrote it as B times q to the G plus 2 because the size of the family is q to a constant times q to the G plus 2. And then we have a power saving error term. Now, using this formula, just like over number fields, we can't actually compute the second moment. So if we use an upper bound for the L functions, a Lindelof bound, for example, for the L function, and we upper bound the second moment, then we can show that more than q to the G times 1 minus epsilon of these L functions are non-vanishing at 1/2 for primitive cubic characters of genus G. So this is the equivalent of x to the 1 minus epsilon. So notice that this is still not a positive proportion. So if we directly use the first and the second moment, the information that we have about the second moment as an upper bound, then we do not get a positive proportion of non-vanishing. The result that I just mentioned, the q to the G times 1 minus epsilon result, was strengthened a little bit by Ellenberg, Lee, and Schusterman using different techniques. So they used algebraic geometry techniques, and they showed that more than q to the G over square root of G of these L functions are non-vanishing. And notice that again, we don't have a positive proportion of non-vanishing. And it turns out that computing the one-level density of zeros in the family also doesn't yield a positive proportion of non-vanishing. So I mentioned in the quadratic case that in joint work with Hang Bui, we showed that more than 94% of the L functions are non-vanishing, and we did that by computing the one-level density of zeros. And for many families of L functions, actually computing the one-level density of zeros provides the best proportion of non-vanishing that we have. But one interesting thing here is that actually computing the one-level density of zeros for this family of cubic L functions doesn't work at all. However, very recently with Chantal and Mathilde, we show that if we work again in the non-Kummer case, so Q is congruent to 2 mod 3, then the number of primitive characters, cubic characters with conductor of degree G, is bigger than some explicit constant C times Q to the G. So we do get a positive proportion. And I should say that this explicit constant C, I didn't write it down here, it's really, really small. However, it is a positive proportion. And the same ideas should work when Q is congruent to 1 mod 3. And the same ideas should transfer to the number field setting as well, but in that case, the results would be conditional on the generalized Riemann hypothesis. So let me talk a little bit about the ideas in the proof of this result. As I mentioned before, we don't know how to compute the second moment in the family of cubic L functions. So if we want to use Saundara-John's approach of computing the first two mollified moments, we can't do that, because computing the second mollified moment is more difficult than computing the second moment, and we can't even compute the second moment. However, one observation is that if we want to get a positive proportion of non-vanishing, we don't really need an exact formula for the second mollified moment. We don't need an asymptotic formula for the second mollified moment. It's enough to get a sharp upper bound. So then the strategy is to define a mollifier, m of chi, which, let me remind you, this kind of behaves like 1 over your L function, so that when we compute the first mollified moment here, we get that this is asymptotic to some constant times Q to the G, where Q to the G is the size of the family. And when we look at the second mollified moment, we can upper bound it by some constant times Q to the G. And then if we use Cauchy-Schwarz, then we get our positive proportion of non-vanishing, which is R squared over S, where R and S are the constants which go in the asymptotic formula for the first mollified moment and the upper bound for the second mollified moment. Okay, so now there are two parts to this proof, and they are very separate from each other. So the first is obtaining this asymptotic formula for the first mollified moment. The second part is getting the sharp upper bound for the mollified moments. So I will talk about the different techniques that we use. I will start with the sharp upper bound for the mollified moments. So here we use ideas from a number of papers. So there's work of Saundara-John who obtained almost sharp upper bounds for moments of the Riemann zeta function, conditional on the Riemann hypothesis. And then his work was refined by Harper, who obtained sharp upper bounds for moments of the zeta function, again conditional on the Riemann hypothesis. And recently, Lester and Radziwill obtained sharp upper bounds for the mollified moments in the family of quadratic twists of modular forms, again conditional on the generalized Riemann hypothesis. So the way we prove our sharp upper bound relies a lot on ideas from these papers. Okay, so the starting point here, the key inequality, is an inequality for log of the absolute value of the L function. So this is also the starting point in the proof of Saundara-John on almost sharp upper bounds for moments of L functions. So the point is that we want to upper bound the log of the absolute value of the L function by a sum over primes. In fact, we upper bound it by a sum over prime powers. Here we have the sum over primes. So I have flexibility in how long this sum is going to be. Let's say we truncate at some point n. Then we have the contribution from primes square, which I wrote over here. And this is the only place where I actually wrote the contribution from prime square. From now on, I will ignore it, although it's not necessarily very easy to deal with it. Then we have this term g over n, which sort of comes from the fact that we are truncating here at the point n, and we have some constant, which some big O of 1 term, which comes from higher powers of primes. So once we have this inequality, we can think of n as roughly, let's say, g over 1,000. So it's some small constant times g. Then we sort of upper bound, so I put this in quotes because it's not quite true, but we sort of upper bound the absolute value of the L function by the exponential of this sum over primes. So now we think of this as the sum over primes, but really we want to have a Dirichlet series. So what we want to do is to truncate in the Taylor series of this exponential. So we use this inequality for the exponential. We upper bound the exponential in terms of a truncated Taylor series. So if we do that, then we are led to consider sums of roughly this form. So I'm summing over polynomials f, whose primes all have a degree less than n. Since I'm truncating at the point L in the Taylor series, this means that the polynomials f have at most L factors. So this is what omega of f means here. Omega of f denotes the number of primes of f with multiplicities. And here we get the character chi of f. We have some combinatorial function here, nu of f, and we divide by square root of the norm of f. So this is what we get from using the truncated Taylor series. And this function here, nu of f, it's a multiplicative function, which is, for example, equal to 1 on primes. So once we have this sum that we need to deal with, how do we define the mollifier? Well, one idea is the following. So we started with the exponential of the sum over primes. And we said that we want our mollifier to behave like the inverse of your L function. So we can think of the mollifier as behaving like the exponential of minus the sum over the primes. And then sort of using this inequality, we can think of defining the mollifier in terms of the truncated Taylor series at the point L of the exponential of minus the sum over the primes. And this would lead us to define the mollifier as the sum over polynomials f with the same properties as before, that all the primes of f have degree less than n and that most L factors. And we throw in the Mobius function here, lambda of f. So the Mobius function is a completely multiplicative function, which is equal to -1 for a prime. Okay, so we because of this, sorry, not Mobius function, Liouville function. Because of the Liouville function in here, we expect to get some cancellation between the mollifier and the L function. So if we do this, what do we get? Well, with this choice of mollifier and our choice of n, the point where we truncate, we would get that the second mollified moment is bounded by q to the g times log g to some constant. So notice that this is too big because we want to get that this is bounded by q to the g times a constant. So maybe we can refine our argument a little bit. Let's see that now we split the primes into two intervals. So here the problematic term is the contribution from small primes, because that contribution can be relatively big. If we look at higher primes, then that part should be fine, should be smaller. So let's say that we split the primes into two intervals, I0 and I1. Again, n is roughly, let's say, g over 1,000, and I0 contains primes with degree between 0 and, let's say, g over log g. Then sort of exploiting the fact that for the primes, for the smaller primes on I0, since the sum is shorter, we can compute more moments. If we run the previous argument, we can show that the second mollified moment is bounded by q to the g times log g to some constant. So this is still not good enough because we want to get just q to the g times a constant, but notice that we gained a log factor from what we had before. So instead of log g, we now have log g. So we can kind of see where this is going. If I split my primes into three intervals, I would get log g to some constant. So then how do we define the mollifier? We do it similarly as Lester and Radziwill did for the family of quadratic twists of modular forms. of a modular form, we split our primes into roughly log g intervals. And then this is how we precisely define our intervals, how we divide our primes. And for each interval, we choose a different Lj. So a different point where we truncate in the Taylor series of the exponential. Okay, and then we define the mollifier on each of the subintervals. So in some sense, Mj of chi mollifies the contribution from the interval ij. And then Mj is kind of what you would expect. So here we have the Liouville function, lambda of f, which takes care of the cancellation between the mollifier and the part of the L function coming from the interval ij. And then our mollifier will be the product of all these pieces. And with this with this choice of mollifier, the argument works. So now we will get that the second mollified moment is bounded by q to the g times the constant. Okay, so this is all I'm going to say about this part of the proof. This is the second, the sharp upper bound for the second mollified moment. Now I want to talk about the first part of the proof, which uses completely different techniques. So now we are computing the first mollified moment. So we have our choice of mollifier. I showed you what the mollifier is. And then we want to compute the average of L1/2 chi times m of chi as we sum over these primitive cubic characters. So computing the first mollified moment reduces to computing roughly a twisted first moment. So it reduces to evaluating the average of L1/2 chi twisted by chi of h for some polynomial h, which comes from the mollifier. And if the mollifier is short enough, then the polynomial h has small enough degree. Okay, so now I want to give a little bit of background on how we actually define these cubic characters over function fields. So let's say that we are in the Kummer setting when q is congruent to 1 mod 3. This means that we do have the cubic roots of unity in fq. Then how do we define the character? Well, we fix an isomorphism between the complex cubic roots of unity and the cubic roots of unity in fq. Then if we have a monic irreducible polynomial p and some polynomial a in fq of t, then we have that a to the norm of p minus 1 over 3 modulo p. This is congruent to a cubic root of unity in fq. And then we look at the preimage of that cubic root of unity in fq through this map omega, and we get some element alpha. So this is how we define our cubic character. Chi p of a is equal to alpha when p doesn't divide a, and it's 0 if p divides a. And then we have the cubic residue symbol modulo p, and we extend this multiplicatively. Okay, now how do we actually compute the average of the L function? So from now on, I'm just going to talk about the first moment untwisted. So over here, I'm assuming that chi of h is 1. The ideas are similar if we have the twist in here. So how do we compute that? Well, a natural question is, how do these cubic characters over fq of t look like when q is congruent to 2 mod 3? So we don't have the cubic roots of unity. It turns out that we can actually express these primitive cubic characters in terms of the cubic residue symbol in a quadratic extension of fq of t. So we can express them in terms of the cubic residue symbol, chi f, corresponding to a polynomial in fq squared of t, which is square free, and it has the property that it doesn't have any prime divisor, which is in fq of t. So all the prime divisors of capital F are in fq squared. And then our sum over primitive cubic characters over fq of t becomes a sum over elements of fq squared of t. And they have this property that the conductor is square free with this property that if p divides f, then p is not in fq of t. So this is the quantity, this quantity on the right-hand side is the one that we need to investigate. Okay, then the next step is pretty classical. So we want to use the so-called approximate functional equation of the L function. So what does this mean? Well, the L function, I told you before that in this setting, the L function is a polynomial. And the polynomial has a degree roughly g. because the conductor of the character has degree G. What the approximate functional equation allows us to do is to write the polynomial as a sum of two terms. So instead of going all the way up to G, I will truncate at some point A, so I get a shorter polynomial. And then I get a dual piece. So the second piece now will go up to size roughly G minus A. Okay, so I have two pieces whose length combine to give G, which is the degree of L. But now I have some flexibility in how I can choose this parameter A, and both sums are shorter than G, which will help us. Okay, so here we have this main term. Here we have a dual main term, so the dual sum goes up to size roughly G minus A here. And I have this object omega of chi f, which is the root number, which I told you has absolute value equal to 1. And it comes from the functional equation of the L function. So our strategy is to get an asymptotic formula for M1 and to get an asymptotic formula for M2. And we will use different techniques to evaluate these two terms. Now, evaluating the main term M1, this is a relatively standard computation, so I rewrote the term here. Recall that chi f, this is the cubic residue symbol in FQ squared, this is a cubic character, okay? So the third power of this character is equal to the principal character. So if I have h equal to a cube, then chi f of h will be equal to 1, if capital F and h are coprime. So we can guess that the main term comes from cubes, and that is indeed the case. So if we evaluate the contribution from cubes, let's say that h is equal to k cube, then I get this double sum over here, and it's a relatively standard exercise to compute the asymptotic for this. We get our main term of size q to the g over here. Then interestingly, we get a second term, which has size q to the g minus a over 6, where a is the point where I'm truncating in the approximate functional equation, and then we get a good enough error term. And we also bound the contribution from non-cubes, and we get a pretty good error term, and we do that using the Riemann hypothesis. Okay, so we have the asymptotic formula for M1. Now, if you look at the formula a little bit, we have this term q to the g minus a over 6, which depends on the point where I'm truncating. So you wouldn't expect such a term to persist in the final asymptotic formula for the moment. Okay, since this parameter a I can choose no matter how I want to. So our strategy will be to compute M2 and hopefully show that that term of size q to the g minus a over 6 cancels out. Okay, so I rewrote M2 over here. We have the character and we have the root number, which has absolute value equal to 1. So how do we express the root number? It turns out we can express it in terms of cubic Gauss sums. So let me quickly tell you what cubic Gauss sums are. So if we have a Laurent series with coefficients in FQ, then we first need to define the exponential. The exponential e of a is defined to be e to the 2 pi I times the trace of a1 over p, where a1 is the coefficient of 1 over x in the expansion of a, and q is a power of p. So this is the exponential defined by David Hayes. And then we have our cubic Gauss sum, which is defined in analogy with the way we would define the cubic Gauss sum over number fields. So g of vf, this is a sum over a polynomial u mod f, of chi f of u, this is our cubic character, times the exponential of uv over f. Okay, and then the root number, omega of chi f, will be expressed in terms of the cubic Gauss sum associated to the polynomial f over fq squared. So this is what it means here, gq squared. We're working over fq squared. Okay, so with this expression for the root number, it turns out that we need to understand this term. So over here, I have a sum over an average of cubic Gauss sums. So I sum g of hf. Now h is fixed and I vary the second parameter, the capital F. It turns out that these cubic Gauss sums have some very nice properties. They're what we call almost multiplicative. So this means that if I look at two coprime polynomials, f1 and f2, then g of v f1 times f2 is the product of the g of vfi's, but we have to twist by this character here, k f1 f2 squared. So if I didn't have the character, I would have that the Gauss sum would be multiplicative. And this is what happens for quadratic Gauss sums. And this is one reason why it's usually easier to deal with quadratic characters than it is with cubic characters. So it's easier to compute moments of quadratic L-functions than cubic L-functions. Okay, so now we want to study the generating series of these cubic Gauss sums. So again, for a fixed polynomial h, we are summing the second variable f, and we want to understand the sum of g of hf u to the degree of f. As we sum over monics, so we sum over the second variable. So this was studied by Hofstein and Patterson using the theory of metaplectic Einstein series. It turns out that this generating series has a lot of nice properties. In particular, it has, for example, a functional equation, and we can show that it has a pole when u cube is equal to 1 over q to the 4. So what we do in order to compute our term here, m2, is that we need some very precise formulas for the residue of this generating series psi h of u at the pole u cube is equal to 1 over q to the 4. So this...
Hi, Alexandra.
Yeah.
We started late, so you have still some more few minutes, but maybe another 5 minutes or so.
Yeah, so I was planning to stop in like 2 minutes maybe.
Perfect, thank you.
Yeah, this is what we do. We compute the residue of the generating series when u cube is equal to 1 over q to the 4, and doing that allows us to get a precise formula for this dual term m2. So we show that m2 is of size roughly q to the g minus a over 6. So again, a is the point where we truncate in the approximate functional equation. And let me remind you that we computed m1, which was asymptotic to a constant times q to the g. And then we had this term of size q to the g minus a over 6. And the miracle is that these two terms cancel out, which is something that we were expecting from the beginning, because we can't have a term which depends on this point where I truncate, which I can choose, which I have flexibility in choosing, but it's still somewhat amazing, I think, that these two terms do cancel out, as they seem to come from very different sources. So for m1, this term of size q to the g minus a over 6 comes from the tail of some Dirichlet series. In the case of m2, this term of size q to the g minus a over 6 comes from evaluating averages of cubic Gauss sums. So we get this cancellation between m1 and m2, and then all the other error terms are suitably small. So we get our asymptotic formula. So I told you that this is the way we get the asymptotic formula for without the twist. Now to get to the non-vanishing results, we need the mollified moments. So we need to compute the twisted first moment, and there is a relationship as to how big the twist can be. So the twist cannot be too big, and the size of the twist depends on the error term that we get in the formula. And this way we get the precise formula for the first mollified moment. And combining this with the sharp upper bound for the second mollified moment, we get the positive proportion of non-vanishing. And the last thing that I'm going to say is that the constant that we get in the positive proportion result is really small. And the reason for that is that the constant that we get in the sharp upper bound for the second mollified moment is really large. So the method sort of doesn't really allow the constant to be too small. So we do get a very small proportion, but it is explicit nonetheless. Okay, so I will stop here. Thank you very much.